So when we're also talking about modern forces, we have to introduce the electrostatic force, also known as Coulomb's law. So when we're referring to gravitation, we originally came up with this mg equation for the force of gravity near the surface of the Earth. We moved on to Newton's universal gravitational law, and it came up with this new idea of interaction between fields, that there's a radial components to my forces, and now we're introducing electrostatic forces, which is, when we talk about circuits, we'll look at simpler ways of talking about the forces in between charges and other things, particularly electric fields. So first of all, I'm going to write the universal gravitational force, and then I'm going to write the electrostatic forces, so we can talk about a few concepts. But first, gravitational. So negative g m over r squared r hat is Newton's universal gravitation. We've already seen it. We've talked about it several times. G is just a constant. It's called the universal constant. Turns out it's not so universal. Mass between one object to another object, and the distance in between the center of masses. So really quick, we're talking about from here to here. There's the radial value. There's a negative sign. So the force on this object from this object is in this direction. Okay? Now, talking about electrostatic forces, the equation's pretty similar. KQQ over r squared r hat. Okay? So another constant it gets introduced, and this is our electrostatic constant. We'll actually talk about this a little bit later. Interaction between two charges. Interestingly enough, there's a difference in between these two equations. We accept the idea of mass as being a fundamental unit. Kilograms is right on the top. It's a base unit. Kilograms is not something that's broken down in other things. It's an intrinsic property. So when we talk about mass, it's an intrinsic property. When we talk about charge, it's not. And that's just the way things were discovered, an order in which things were discovered. When we talk about charge, we're talking about amps. I mean, amps is the base unit, but it's not a base unit of charge. Base unit of charge is a coulomb. It turns out an amp is 1 coulomb per second. So it's just the order in which things were discovered. We discovered current before we discovered fundamental charges. So when we talk about charge, we're talking about a coulomb, and a coulomb is not a base unit, which is one of those things that upsets me to no end. I mean, we should start writing our National Institute of Standards to say, look, we need to change this. If we can get rid of Pluto as a planet, then maybe we should get rid of an amp as a base unit. Instead, focus on a coulomb, which seems to me like a better base unit. But that's a tangent. Tangent. Cut it off. So here's the interaction. So GMM over r squared, KQQ over r squared. They're both inverse square laws. It looks like the fundamental nature of the universe falls off as 1 over r squared. So all these forces appear to be falling off like that. Here's something that's kind of interesting, though. When we talk about this, 1 kilogram times this value. So 1 fundamental unit of mass, another 1 fundamental unit of mass. 1 and 1 times together gives me 1 times g gives me a certain amount of force. Well, it turns out that the g here has an order of magnitude to the negative 11th. So 10 times 10 to the negative 11th. So times 10 to the negative 11th, that's the size of it. Pretty small. All things considered, it's pretty small. But it's interesting that we consider gravity to be one of the strongest forces in the universe. It's actually one of the weakest. The reason why we take gravity to be such a strong force is because there's no counter to it. I don't know if I've mentioned this before. We don't have a negative mass value. Everything we know so far, I mean, there's some theories out there talking about negative mass. Everything we know so far are only positive values, so everything is retracted. No repelling, excuse me. K, on the other hand, has an order of magnitude to the ninth. So 1 coulomb times 1 coulomb, okay, is going to give me a strength that's almost 20 times, or 10 to the 20th power time, not 20 times. How about, oh gosh, more than a billion. A billion billion? A billion 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 times more stronger than the force of gravity. A tremendously powerful force. When you look at, you gotta quit touching that cart. When we look at this, the relative strength in between these, it's a huge difference. So why don't we view electrostatic forces as being a stronger force? Simple. There's a counter to it. You got protons and you got electrons, a negative and a positive charge. If I get a proton and an electron together, they're attracted to each other. I get a proton and a proton together, they're repelled. So if I have a proton and an electron and a proton and an electron, we've got ourselves a little bit of stability there. Where if it was gravitational forces, I have 1 kilogram of mass, 1 kilogram of mass, they're attracted to each other. Okay, they're always attracted to each other. Where we can counteract each other by introducing the opposite charge. We're talking about electrostatic forces. Okay, so it's a tremendously powerful force, but it has that opposite charge, and that, you know, we can deal with counteracting a negative charge with a positive charge acting towards each other, a negative charge and a negative charge repelling towards each other. So we've got all these interactions, so it allows us to cancel each other out. Okay? So Coulomb's law, really quick, KQQ over R squared, interaction between charges. Okay? And these are coulombs, but they're not base units. Don't forget that. They're the base unit for electrostatic anything turns out to be an amp. We'll talk about that when we get into circuits. Okay? Cool? Now, the other thing I want to talk about is K. K represents a constant, right? So it's a constant. It's not, you know, like the universal constant here, G. But we refer to it as K because that constant actually has another equation to it. That constant turns out to be 1 over 4 pi epsilon. Okay? That K equals this. And there's actually it's really important to have that floating around. This epsilon is actually called the permeability constant. It's how well electrostatic fields move in space. Okay? But it turns out that epsilon has other properties when we talk about the speed of light. But that is actually the real equation. You know, substitute that in for K, so you get QQ over 4 pi epsilon R squared R hat. Is actually the traditional way of writing that equation. We just say, well, epsilon is pretty much this. That permeability constant really doesn't change that much in the atmosphere. So we're just going to leave it as K. Okay? Just another way of expressing it. But that's Coulomb's law. Cool? Alright, so I'm going to talk